Hi, I'm Jordan Snyder, and today I want to talk to you about fitting an ordinary differential equation, or an ODE, model to data. So the situation that we're thinking about today is that we have some data, and our data are of the form ti, xi, I running from 1 to n, where t we can think of as a time variable and x is a state variable. And the situation is that we believe that we can describe the x's according to a differential equation that they obey with respect to time. So just to give a little bit of a visual on this situation, we could imagine plotting x over time and say we have some points like this. So we believe that the time evolution of x is described by a differential equation, and we'd like to find out what that differential equation is. So to do this, we have to specify a model class. In this case, I'm going to suppose a very concrete physical model class, which is a spring, a mass on a spring with a damper. So our model, this is known as a spring mass dashpot system. And physically, the way this is usually depicted is with a little drawing like this. So we've got a wall connected to a spring. That spring is connected to a mass. And that mass is also connected to this funky thing, which is called a dashpot. So that's damping. So physically what's happening is that the spring gives a restoring force. So it brings the mass towards the equilibrium point, and then the dashpot slows the mass down. So the differential equation that describes the motion of this system is Newton's second law, F equals ma. So if x is the position of the mass at any given time, then the mass times the acceleration, which is mx double dot, here dot represents the time derivative, is equal to force. So what is force? Well, I've got a force from the spring. That's modeled by negative k times x. And it's also got a damping force. And that's modeled by negative c times x dot. So the faster the mass is moving, the more damping force is going to be experienced. Okay, so this is our differential equation. So it's second order in time, and it involves x and x dot on the right-hand side. In this case, I'm going to make a simplifying assumption and just say that the mass is equal to 1. So it's a 1 kilogram mass, or in other words, I choose mass units so that the numerical size of the mass is equal to 1. And that just makes our calculations a little simpler. So the problem, in effect, now that I have this model written down, is to figure out which values of these parameters, k and c, fit the data best. Now, to do this, we're going to need to computationally solve the differential equation in code. And to do that, we need to present it as a system of first-order differential equations. And the way that we get there is a very simple mathematical trick. So what we do is we introduce a new variable called v for velocity, and we say let x dot be equal to this new variable v. And then v itself obeys another first-order differential equation, v dot. And what is v dot equal to? Well, v dot is x dot dot, so it's x double dot. So v dot is equal to this right-hand side right here. So it's equal to negative kx minus c x dot, which of course is equal to v. So just that simply, I've gone from a scalar second-order differential equation to a system of two first-order differential equations. And this trick is super common, and it can even extend further. So if you have a third derivative, you can introduce a third variable and get 3 first-order differential equations. In general, you can go from an nth-order scalar equation to n first-order equations. Good. So we've got our first-order system of differential equations. And now, our question, we've got our system of two first-order differential equations. Now our question is, what parameter values k and c and initial conditions x0, v0 agree best with the data. Okay, that's the problem that we're trying to solve. Now, how do we actually formulate this mathematically? Well, what we're going to do is I'm going to treat these unknowns as a vector of 4 elements. So I'm just going to say theta vector is the vector of x0, v0, k, and c. And I'm going to write up a minimization problem over the variable theta. So what I want to do is find the minimum over choices of theta of the following quantity. Now I want the solution to the differential equation that I'm thinking of to be close to all the data points. So the thing I want to minimize is the sum over all data points, I going from 1 to n, of the discrepancy between the data and the ODE solution. And the way I'm going to write that is xi, the data point, minus x sol of ti semicolon theta squared. So I'm minimizing the sum of squared residuals, and the residuals between the data and the ODE solution. So this here is the ODE solution. Okay, so this is a somewhat complicated nested problem. So I need to do a function minimization over this function of theta. And to compute this function of theta, I actually need to go ahead and solve a differential equation inside the loss function. So there's several steps to do this, and I'm going to show you how to do that in Matlab, and then later on I'll show it also in Python for comparison, and I'll put a timestamp below so you can skip straight to the Python if you'd like to see that. So let's jump into the Matlab code. The first thing I want to do is generate some data. And just like in the curve fitting video, if you saw that one, I'm going to generate data from a system of the model class that I'm considering so that I have a good chance of actually recovering the true model. So let's set that up. So I'm going to think of my ODE system as a system of 2 first-order differential equations. And the way that MATLAB and most software packages handle a differential equation is that you tell it the right-hand side. So it assumes that you've solved for the first derivatives on the left, and it wants you to give a function of your state variables, here x and v, that gives out the time derivatives, so the right-hand side of your equations. And that's done in this function called ODE fun. And when you define an ODE, the function that you use to define it has to have a predictable calling signature. So this function has to take time as its first input if your right-hand side depends explicitly on time. So say if you have a forcing function, the function needs to accept a time input. In this case, the right-hand side does not depend on time, so I put a little tilde there. And that just says to MATLAB, yes, this function takes an input, but it doesn't use it. If you put t there, but then don't use it in the function, the code editor will give you a little warning that says, hey, this function takes an input, but it doesn't use it. So anyway, it's a small detail, but it's there. And then the second input is y, so this is an array variable that contains x and v, so it's a 2-dimensional array. And then the later arguments are parameter values, so here's k and c, the spring constant and the damping constant. So what the function does is it gives me out a vector of x dot v dot. So according to this system of equations, x dot is equal to v, so that's the second component of y, and v dot is equal to negative kx minus cv. So here x is the first component of y and v is the second component. So this is a variable I'm calling dy dt, and that's the output of the function. Now I'm going to then solve the equation and then add some noise to get my data. So to solve it, I need to specify certain things. I need to specify the time span. Here I've just chosen 0 to 20 and an initial condition. So this is x0, v0. So I'm starting at a position of 1 and a velocity of positive 1. And I've chosen some parameter values, so k is equal to 1.5 and c is equal to 0.25. Then to solve the equation, I'm going to use a built-in ODE solver that comes with MATLAB. It's called ODE 4.5. This is a Runge-Kutta method of mixed 4th and 5th order. I'm not going to get into the details of what exactly that means, but it's a good choice for a first try at solving your equation. Sometimes it has poor performance on problems that are what's known as stiff. So if the right-hand side of your equation depends very sensitively on the values of your state variables, then your equation might be stiff, and it might be ODE 4.5 might be unsuitable to solve it. But in a lot of cases, ODE 4.5 will do just fine, and in this case, it does just fine. So what does ODE 4.5 take? It takes a function. So that's something that you might have to wrap your head around if you've never done this in code, is that you're defining a function and then you're passing it to another function. And that's sort of essential when you want to solve a differential equation, because a differential equation is defined by a function. So the function that it's taking, ODE 4.5 wants the function to accept two inputs. It wants the function to accept t and y. But we also have parameter values. So the way that I'm doing it here to pass in parameter values is passing in as an argument an anonymous function. So this notation in Matlab defines a function inline. So what's written here is at ty, so this is saying the function that takes inputs ty and gives as output ODE fun, where you've passed in ty, and the other two inputs are k and c, which have been defined outside of the function. So yeah, this is a sort of common trick when you want to fix the values of certain extra inputs and treat the function as a function of fewer inputs. So that is the first input of this function, and then I also specify the time span and the initial condition. And then MATLAB will solve this differential equation. Then it'll come to plotting the differential equation. And to do that, I specify a grid of time points where I want to evaluate the solution. Here it's a linspace, so this is an evenly spaced grid from 0 to 20 with 200 points. And then to get the y values, I'm using this function, which is deval, so it gives the values of a differential equation, and what you give it is the solution object that comes out of ODE 4.5 and the time points that you want. So this output of ODE 4.5 is a very rich object. It knows how to estimate the value of the solution at any time point you want to give it. So you're not fixed to a particular grid of time points. So that's a pretty nice feature to know about. So at this stage we have a grid of time points and a list of y values, and then I can simply plot it. So let's run this code. Oops. And here we go. So what we see is oscillation with damping, exactly as we should expect. So we have the spring and the damper, so the mass has initial value 1, initial speed positive 1, so it's moving away from the origin, and then it oscillates back and forth, and the damper extracts energy out of the system, so it's becoming smaller as time goes on. Okay, great. So now this is our true dynamics. Now we have to get some data that we're going to then apply the fitting procedure to. To do that, I'm going to select some random time points between 0 and 20 and get the x values of those time points and then add some noise. So here I'm specifying n data, so that's how many data points do I want. In this case, I'm choosing 50. And to get a random selection, the way I'm doing that is randomly permuting the numbers 1 to 200 and taking the first 50 of those numbers and then finding the time points at those 50 indices. So this is what I'm doing here. I'm randomly permuting the numbers up to length of t, which is 200, and then selecting 50 of those. And then I'm sorting them. So I get 50 random indices between 1 and 200, and I want to put them in order so that the time values I get subsequently are in order. So that's what I'm doing, and then I'm taking t data as my time array evaluated at those indices, specifying a noise level, in this case 0.1, and then here's where I get my y data. So here, notice that I'm picking y in the first index, so that is the x component rather than the v component, and then idx specifies which time points. And then I'm adding noise, so this is a random vector of Gaussian distributed noise times the noise level. So let's see how that looks. So here in orange, the color has switched. Now x is orange, and these little blue dots are my data points. So imagine that I don't see the curve, all I see is this data, and I want to fit my ODE to it. One thing to note here is now this is an incomplete measurement. I've not observed anything about the velocity, so my measurement is actually incomplete. But even though it's incomplete, I'm still going to be able to solve this problem and get a good solution. So let's see how that works. Now, we have our data, so we want to now set up this minimization problem. The core of this minimization problem is this ODE solution. So I want to write up a function in Matlab that actually does this calculation, so that can get the solution to the ODE at a given parameter value at a given time. So to do that, I've written a function that I called forward model, and it takes param values, that's theta, and time values, that's t data, so ti. So what this function does is it takes the param vector and unpacks it. So the first element is x0, then v0, then k and c. Oh, except here I've called them a and b, but it's just the same. Then it sets up the ODE solution procedure. So it gets a t-span, so it decides I want to solve the ODE on the range of time values that includes all of the time points that you give it. So that's the minimum of t data to the maximum of t data. And then it calls ODE 45 in just the way that we did before. So it's an anonymous function with ty mapping to the ODE fun of ty with parameter values a, b. So this is how the parameter values get from the parameter vector into the ODE solve. Then we also need to specify the time span and the initial conditions. So this is how the initial conditions get from the parameter vector theta into the ODE solve. Then finally, I need to compute the outputs. So I take the solution object and evaluate it at the t data points that I have. That'll give me, actually, so I'm taking the full solution, so this gives me x and v, but I'm actually going to just be comparing to x. Okay, so this is how I write a function to compute x sol. Then I want to compute this function. So this is the loss function, the sum of squared differences between the data and the ODE solution. So that's being done in this function called loss. So it takes as input parameters, t data, and y data. So y data, these are unfortunately called them y data in the code, but they're x's over here. But these are the xi values. And what this function does is it runs the forward model with the given parameter values and the time points. And then it's summing up the square differences between the first component, so that's the x component rather than the v component of the model solution, minus the y data, and then it's squaring these. So this is the element-wise square. And then I'm summing up over all time points. And then it's returning that as the loss value. So all that's left to do is carry out this minimization. Now, in general, this is a very tricky problem to do, but I'm not going to go into the details of how the actual optimization function works. What I'm going to do is just call this function that's built into MATLAB called fminsearch. This is a derivative-free method. So yeah, in general, optimization methods can be either derivative-free or they can use the derivative of the loss function. If you actually have access to the derivative of this with respect to theta, you can, for example, compute the gradient and then follow the gradient to find directions in which the function increases or decreases according to whether you want to min or max it. But in this case, we're not going to touch differentiating this with respect to theta. We're just going to use a derivative-free method that will basically search the input space in a systematic way and return us an estimate for the minimum. So that's what fminsearch does. And the things that fminsearch needs is the function that you want to minimize and an initial guess. So what fminsearch is getting, so here's my initial guess, and I've just given some values that happen to be pretty close to the values that I know to be true. I want to give it a good chance at finding the real solution. And fminsearch, so it takes a function And that function is the function that takes theta, the parameter vector, and gives you out this loss function evaluated at the parameters with the t data and y data. So that's the function it's trying to optimize, and then the initial guess is x0. So this function goes and does a whole lot of computation. It evaluates this function over and over again. Each time it evaluates the loss function, it has to solve an ordinary differential equation. But it'll do all of that all by itself and then return to you with an estimate for the optimal value. So let's run this code and see what we get. So it runs quite fast, which is wonderful, and we get 1.2, negative 0.01, and something close to 1.5 and something close to 0.25. Okay, so let's go and see how well we did in terms of actually comparing the ODE solution to the data. So to do that, I'm going to take this parameter vector that I got out and compute a dense solution, so a solution that'll sort of go through all time points in between the data. So I've got the full solution. This is the same function as I already defined before, and I can run it, get a full solution. And then my data points here, now these are in yellow circles, and the curves are the full solution evaluated at the parameter values that I found from my minimization. And we can see that this looks really good. Okay, so we ended up with quite a good fit between the data and the true solution. The way we did it was by taking our ODE model, presenting it in a form that Matlab can understand well, and then writing up a loss function that involves the ODE solution, and then minimizing. So that's it for the Matlab section, and now I'm going to reset a little bit and go into the Python implementation. Okay, so here we are with Python. So now we're going to do exactly the same procedure that we just did with Matlab, except in Python. So I'm not going to explain this in quite as much detail, but a lot of the considerations are just the same. So we still have to pass a function to a function in order to solve the differential equation, and we need to pass a function to a function in order to minimize this loss function. So the way this works in Python, I'm going to get my imports. So I'm using NumPy, Matplotlib, and SciPy. And SciPy is the package that is going to provide my ODE solve. So it's the solve IVP command, IVP for initial value problem. And it's part of the SciPy integrate package. I'll run this. Okay. Now, just like I did in Matlab, I need to define the ODE system. So here's ODE fun. Again, it takes t, y, and parameter values and gives out a vector of the time derivatives, so the right-hand side of our system. You'll notice that Python is 0 indexed rather than 1 index, so I have y0 is the x value and y1 is the v value rather than y1 and y2 as we had in Matlab. So I have my right-hand side, I have my initial condition, and I have a vector of arguments. So here I have 1.5 and 2. So this is the same parameter values as I used in the Matlab case. Then I'm setting up the time span and the size of the time grid that I want to use. So I have 0 to 20 with 200 steps. And then I'm going to solve the IVP with the ODE function, the time span, the initial condition, and then in Python, the way that the solve IVP function works is you can actually pass a keyword argument called args, and it will give the ODE function the extra arguments that it needs. So this is a little bit of a difference in how the programming works between Python and Matlab. And finally, I'm specifying this flag dense output equals true. So that gives us that feature that we had in Matlab where we get a solution object, and then later on we can evaluate the solution at any times that we want. Okay, wonderful. So then I'm specifying a vector t eval. So that's my linspace. It's 200 points evenly spaced from 0 to 20. And then I'm going to plot the solution. So here's my solution. Again, it's oscillation with decay. And then I'm going to generate some data by taking this X curve and sampling it at randomly chosen time points and then adding noise. So random number generation in Python, at least in the NumPy package, is done by creating an RNG object. And then you can use that to sample whatever kind of random numbers you want. So here I'm taking, there's a choice function. So if you want to choose one item randomly from a collection. You can pass a collection and tell it how many items you want and whether or not to replace. So I want all these time points to be unique. So I'm saying replace equals false and size equals 50. So I want 50 time points. And then I'm getting y exact by taking the solution values at those t data time points. And then this extra 0 over here, that is taking the first state variable rather than the second, so x rather than v. Okay, so this is exactly the same as I was doing in the other example. Again, now I have a noise level, 0.1, and then the noise is noise level times some standard Gaussian random variables, and y data is y exact plus noise. If I run this, then what I get is some dots for my data points, and then these curves are the exact solution. They just look a little bumpy because now I'm only plotting them at the t data time points. Okay, so yeah, don't mind that they look a little jagged. Okay, but at this point we have data that's represented by these dots, and we'd like to fit an ODE to them. So we have to define the model. The way I'm doing that is by, just as before, I'm going to write a function called forward model. It takes parameter values and time points and gives out xsol at those time points given those parameters. So what I'm doing, this is, how would I say, array unpacking. So params has 4 entries, and this is a way to tell Python just to take those 4 entries and place them into x0, y0, alpha and beta. So I've given these different names, but these are just x0, v0, k, and c. Then create a time span that spans over the times that I need, so the minimum that I have in my data and the max. And then the initial condition is x0, y0, so that should be x0, v0. And then the output is the solve IVP of the ODE function over the specified time span with the initial condition and evaluated at the t data time points with the specified arguments. Okay, so this gives me just exactly the ODE solution at the specified time points. And finally, what I'm going to return is just the x component, not the v component. So I take the output and take the y attribute of the output is just the solution part, and the 0 entry of that object is the x component rather than the v component. The v component would be y1. So I'm going to define that function. Now I'm going to fit the model. So to do that, I need to define this function, define the loss function. The loss function takes as input parameters and data. So parameters theta and t data, y data. So what the loss function does is it generates a model prediction, that's xsol, and then returns, I'm using the linear algebra norm, so that's the same as the sum of squares except for normalization constant. And I'm taking the norm of the difference between the model prediction and the data. So that is the function that I need to pass over to my optimization procedure to get a solution. So the last thing I need to do is pass the function in, and again I need an initial guess. So here's my initial guess. It's the same or nearly the same initial guess as I used in Matlab. And then I'm using the scipy optimize.minimize function. So this is a generic kind of function, and you can tell it to use any number of different optimization procedures. And if you don't, it will choose sort of a reasonable default. And what is it that I'm minimizing? I'm minimizing the function that takes as input a parameters vector and gives out the loss given those parameters and t data, y data. And my x0, this is my initial guess, and I'm giving it a method, and the method I'm using is called Nelder-Mead, so this is also a derivative-free optimization method. And finally, I'm going to print the output, so we'll talk about what that is. So here the result, this is a compound object with a lot of information about how the optimization process went. So it has a flag for success, so it says this optimization was successful. And then the most important entry of this is x, so this is the minimizer. This is the value of theta that I believe minimizes the loss function. So we have something around 1, something around 0.6 or 0.7, around 1.5, and around 0.25. So that's all well and good, but let's go and bring this together and visualize it, the fitted model against the data. So what we have here, this curve, is the model fit, and the dots are the data. So just as before in Matlab, we see what appears to be an excellent fit to the data. So we have good confidence that the parameter values that we got out accurately describe the data that we measured. So I hope you enjoyed this lesson. I hope you learned a bit about how to mathematically manipulate an ODE system and translate it into code in a way that Matlab or Python can understand and give you a solution. And thanks a lot for watching, and I'll see you next time.